Okay, this is lesson 23 for geotrig. We're going to graph exponential functions. Exponential functions are y equals b to the x form. I'm going to deviate from the book, as in I'm not just going to give you really simplistic exponential functions. I'm going to throw everything at you for these. I'm giving you the most complicated exponential functions that are possible because they all graph the same way. And this way we're going to graph them is using the parent-family-child method. Some of you guys have seen that, some of you guys have not. But what we're going to do here is we're going to first, on this slide, is kind of set up the fact that what is an exponential graph. There's two different types. There's ones that are growth, some that are decay. And what we're going to do is we're going to be able to graph them. So an exponential graph is y equals b to the x, where b is the base. X is the exponent, right? And b itself, to be an exponential graph, we're not going to just choose any value for the base. And the base, guys, is fixed. B is going to be decided. It's going to be, B is going to be a number that's positive. Doesn't have to be nice. It can be 1.5. It can be the square root of 3 if you really want it to be. But b is going to be a positive number to some power. That's not equal to 0 and not equal to 1. If it was negative, well then if I take it to a power, if it's an even power, that number becomes positive. If it's an odd power, it would stay negative. And it would go back and forth, positive, negative, positive, negative. It would not be an exponential graph. It would be something a little different. And so we stay positive, so it's always a positive graph, or all the consistent there. And it can't be 0, because if b was 0, 0 to any power is 0. Except for 0, right? And if b was 1, well, 1 to any power is 1. So that wouldn't change. The graph would always be the same. So that would not be exponential growth or decay. And so we limit ourselves then to those positive numbers other than 1. And we have them there, two different choices. Now there's supposed to be some graphs in this black box, but for some reason it just didn't give me the picture, it just gave me a black box. So we will try to use a lighter color for this one this time. And if I chose a b value between 0 and 1, so like a half or a third or an eighth, and I raise it to a power, so let's just say a half. If I chose 1/2, what's 1/2 squared? That'd be 1/2 times 1/2, right? That'd be a quarter or 1/4. Is that getting bigger or smaller? Smaller. What if I took 1/2 and brought it to the third power? It'd be 1/8. It gets even smaller, right? So, if I'm talking about the base being a number between 0 and 1, we are actually going to call that decay. Okay? Decay. That would be what we call exponential decay. If the number is bigger than 1, the base is bigger than 1, I am going to call that exponential growth. Take, for instance, 2. 2 squared is 4. 2 to the third power, 8. 2 to the fourth power, 16. It keeps getting larger and larger and larger. Now wait a minute, even think of this. What's 10 squared? What's 10 to the third power? Gets larger quicker, doesn't it? So the bigger the base number is, the larger this graph is going to get, or the quicker this number is going to get larger. because we're taking exponents. Now, these graphs look different from each other. A decay graph will start tall, or start out with a lot, and go towards nothingness. But here's the problem, or here's the thing. Can you start with something and bring it to some power to get nothing? No. Okay? So you never are going to make it to 0. Guys, if you buy a car, your car loses its value exponentially on an exponential decay graph. It starts tall. Your car might be $10,000 when you first got it. Drive it off the lot, and it starts to lose its values. Very fast at first, right? The old word is you drive it off the lot and try selling it back the next day, you've already lost a couple $1,000s off your car. And you're like, what? I've only got 3 miles on it. It's lost its value. It's not worth as much anymore.
Not new anymore.
So it loses a lot of value in the beginning, but over time it starts to settle itself out, right? That's exponential decay. Radioactive material does the same thing. Radioactive decay. Half-lives. Exponential growth. Exponential growth works in the other direction. It starts off with a small amount and gets larger. Now, the cool thing about exponential growth is the fact that it may start off small, and it looks like it's just growing a little bit, and then all of a sudden, you get to this point, and it starts getting faster. That is the power of exponential growth, and that's why they tell you if you're going to invest money in the stock market or whatever, you invest it early. Because the longer you let your money sit in there, a savings account or investing it some other way, it grows exponentially. The more money you have, the more money you make. And the more you put in the beginning, not there, here, the more you put in the beginning, the quicker it's going to go up. The higher the percentage of rate of return, the quicker it goes up. Okay? So these do have real world applications. We just don't directly see them. No one sits down necessarily and tells us, here's the equation. We just look at the end result saying, yeah, I want that. Or no, I don't want that. Okay? Now, there are some things about this. I highlighted the fact that if I change B, the graph will change. It's either going to grow faster or slower, right? Well, here's the thing. I know what's happening in this part of each graph. Where's it going? Each one of those little arrows points to where? It's approaching where? It's approaching infinity, but it's going towards this line right here, and that is 0, right? Or the asymptote. Each one of these graphs will never cross that line, which then leads it to be an asymptote. They're approaching 0. So that circled part in yellow, we know that there's a certain part of each one of these graphs that just goes towards 0. The other part of the graph is the ones on the outside, right? The stuff where it either starts really tall and goes down, or starts small and goes up for growth. I don't exactly know where those are going. So, where is this going? Where is that going? Is it? I'll use the growth one. Should it started off and went out more gradually? Or should it started the same way, but yet all of a sudden take off? Which one of those 3 choices was supposed to be the graph? It's hard to tell, right? I would have to start putting values in to figure this out. So what I'm going to do is that I'm going to say, and the same thing goes for the decay. Was it decaying really fast or really slow? We know it's going to go towards 0, but we don't know this other part. And that other part where we're going to say, don't exactly know what's going on, I'm going to call that the tail. Where's the tail going? And so what we're going to do is we're going to set up some really cool things about all of these y equals b to the x graphs will have in common. I'm going to call these parents. Okay? And so these are all parent graphs. All other exponential growth or decay graphs have this quality. They start off the same exact way, following the same thing of y equals b to the x. So, what can we say? If I'm talking about a parent graph of y equals b to the x, okay? They have this in common. They have an asymptote at y equals 0. Look at both of those graphs I have on there. Even the multiple options, they all went towards 0 on half of the graph. So another one of those things that it's less things you have to remember. Asymptotes, always y equals 0. Here's a cool thing. It doesn't matter what I put in for b. Half, a third, a 9, a 10, 1,000. If I bring it to the 0 power, what's the answer?
0.
Not 0.
No,
It's 1. Because anything to the 0 power is 1. So guess what? Wait a minute. That means the point 0, 1 always will be a solution to that equation. Yes?
Yes.
What is 0, 1? That is just another thing. We have a name for those. It's a
Point.
It's a y-intercept. It's a y-intercept. Every parent graph has a y-intercept at 0, 1. And a y-asymptote, y equals 0. A horizontal asymptote. Always. It'll have those two things. Now, where we have to differentiate between the two is that when it's decay, the left side starts tall and goes down. And in its growth, the right side starts low and goes higher, right? So I got to figure out that tail thing. So what we need to do is we need to come up with a way to help us figure out where the tail is going so that we can graph it correctly. Now, this is how I figure it out. I am going to find an extra point. Okay? The extra point, you only choose one or the other, but we need one more point. And that one more point I want on the tail. If it's decay, or if it's growth. So this is your only decision necessarily. It's not a big one, but it'll help us identify the swoop of the curve, we'll call it. Where is the curve being drawn out to? Is it going to be gradual, or is it going to be a steep curve? And if it's decay, the tail's on the left side. What kind of numbers are on the left side of a graph? Negative numbers. Now here's the thing. If I choose a really large negative number, like negative 10, the exponent's going to be a negative 10. What happens when you put a large exponent? The number gets very large, doesn't it? I don't want large numbers. I can't graph 1,000 on this graph. I don't have enough room. So I'm going to stay really close to home. And I'm going to choose a value like negative 1. Now, yes, I did just put negative 1, comma, nothing, or a space. That space is the answer when you place negative 1 in for x. We're going to do a problem that actually has a number for b, okay? This will hopefully get tied together. But I'm placing or choosing an x value that's going to allow me to be able to graph it. Now, for growth, I got to choose a value on the right, and those are what kind of values? Positive. So what value do you think I'm going to choose to put in? 1. I anything to the first power is that thing, right? So that makes it a lot easier. It's simple, small numbers. To graph an exponential growth or decay graph, I'm only asking for three things. An asymptote, which is always going to be y equals 0. A y-intercept, it's always going to be 0, 1. And an extra point that we need to say, it has to be on the tail. If it's decay, it's -1 something. Or if it's growth, I put in 1 to figure out what it is. Okay? So what I want to do here is, I want to graph this. Now there are some things that maybe we should talk about. Is this an exponential growth, or is this an exponential decay graph? It's a growth. Why is it growth? Not because it's positive. Do not think that way. Because what's greater than 1? 2, or B. Guys, B is equal to 2, which is greater than 1. Therefore, it's growth. We have to understand that negatives and positives are not affecting my growth or decay part. It's what is 2? What's the base number? Base number is 2. It's bigger than 1. It's growth.
If it's 1, is it growth?
If it's 1, we don't have an exponential growth decay graph. It's not even an exponential graph. Because the answer will always be 1. So it can't be 1 and it can't be 0, remember. It has to be positive. So if that would have been 1/2, then it would be exponential decay. Now the reason why I identified its growth, that means my extra point, what's the value going in? It's 1. We only have two choices, -1 or 1. Okay. So let's look at that options. There are three things I needed. One was the asymptote, and that is y equals 0. We had a y-intercept, which was 0, 1, and I have an extra point. And the extra point, because we established its growth, I want to find the tail, right? Therefore, I'm going to put a 1 in. Now we have to actually find the other half. How do I find the other half of that point? Plug it into the equation. Take 1 and plug it into here. 2 to the first power is 2. You guys graph those three things, and you're done. Well, after you swoop in the curve. That's it. We are going to explain the parent, family, child part, or start it, and then we'll have to go into examples tomorrow. So, here we go. We know that we have our XY axes. And we know we have an asymptote where y equals 0. Okay. That means I can't cross that, right? Okay, so that means I'm either on top or I'm on the bottom. Y-intercept at
0, 1.
0, 1. And we have the point that's on the tail at 1, 2. What's the only way to connect those two dots so I can't cross the dotted line? So it's going to start low and go up like this. That is an exponential growth curve. We're going to call that a growth curve, yes. Okay. If it was exponential decay, guys, then the point would have been over here somewhere, right? And then you would have went this way.
What's the other graph you drew?
We're not doing that. The other one was just an example saying that it's growth. I want to know what's going on over here. That's the only reason I drew that. You guys don't have to worry about that. Just take it out of your mind. Okay? So are there any questions on that? So now what we're going to do is we're going to take graphs or equations that have all the parts, and I'm going to call it child. And we're going to break all of those down into their parents that look like this. and I'm going to establish those 3 pieces of information. And those 3 pieces of information are then going to be multiplied to and added or subtracted to change it to get the 3 points of interest for the child that I can graph the exact same way. And then I'll have an answer. So, here it is. This is what I call the child then. You guys have the parent, and now we're given a child, and the child is y equals a times b to the x minus h power plus k. Now, what's the difference between a child and a parent is the parent, you take away all the extra stuff, and you're left with what the basic part of the problem is, which is the parent equation. And the parent equation is, and I'll put it back on as soon as I'm here, is taking away the a, the h, and the k. And there's your parent. I strip away what I call all the moving parts. So I'm going to bring that back. Okay? I take away all the moving parts, I get down to a parent. Because if this is what my analogy is that if you're out and about someplace and this little kid comes up to you and starts picking on you or pushing you or throwing stuff at you and being annoying, you don't take care of that situation yourself. Because as a parent, if I see somebody doing something to my kid, you get angry. You don't like that. So the proper thing to do is go up to that parent's family and or parent and say, hey, so-and-so, I have this problem. Your child is throwing stuff at me and I've asked him to stop and it's not working. Okay? You go to the parent. The parent then is going to try to take care of it. If the parent can't take care of it, and this happens, they call the family. They call grandma, grandpa, they do whatever they need to do. They call somebody, and then they go on to the child and we take care of it. Okay? That's kind of the order we're going to do things. We also look at the order that the parent, the family, the child is all coming into play. To go from the parent to the family, the only difference is I bring back what letter? An A. And that A is going to be multiplied. Okay? Go to the child. From the family to the child, what's brought back? H and K. And H and K are added and subtracted. So therefore, what comes first in order of operations? Multiplication or adding, subtracting? Multiplying. So I'm going to multiply. I'm going to do the multiplication stuff first, then do adding, subtracting. Now let's talk about what each of these pieces do. A, guys, A is what we call the amplitude. Amplitude, guys, does this. Amplitude tells you how big or small the graph is going to be. Now, when we say we're talking about a parent graph, we're talking about a whole system or a bunch of graphs that are based off the same one. And that's what we call it the parent. They all look the same. When I get to a family, I bring back the A value. A family of graphs look exactly the same, but one's bigger or smaller than the other. It's kind of like having a mini-me walk around. Okay? It looks exactly the same, but just a smaller graph, or a larger graph. Okay? They vertically stretch the graph if A is bigger than 1. Because if you multiply something by 2, it gets bigger. It's a vertical shrink if it's less than 1, because if you multiply something by half, it's half the size. And it actually can reflect it about the x-axis if it's negative, which means it doesn't stand up tall, it flips down to the bottom. We'll do cases of these as we go through. We then have H. H is my translation, left or right. I'm going to translate this graph left or right. I'm going to pick it up and move it left or right. K is what we call the translation up or down. So I can physically move this up and down. Now there is one more thing that we have to worry about my left-to-right movement. Notice that in the equation it says x minus h. If h is positive, it's actually going to the right. If it's negative, it goes to the left. But it's not what you're thinking as it looks there. I'm going to say it's always opposite of the sign. It's always opposite of the sign. The movement is opposite. What does that mean? That means if you were to see something like x minus 3 in the spot on the as an exponent, I am actually moving 3 to the right. It's not 3 left. You're like, oh, that's a negative 3. I got to go left, right? Because that's negative in the x direction. No. It's because it's supposed to be x minus h. That means h has to be 3, which means h is positive. That's to the right. If you were to see something like x plus 3, that would be 3 to the left, because that means it would be x minus a negative 3. And when you subtract a negative, you are adding. Okay? So, our h and k does that. Translated h units left, right, and translated k units up, down. Our a tells us if it's a vertical shrink or stretch, if it's bigger than 1 or less than 1, and if it's going to be reflected about the x-axis. What we're going to do is we're going to pick up tomorrow. We're going to do examples. We're going to first of all talk about how to obtain graphs, the vertical in words, and then we're going to graph them. So, your homework tonight is just to graph those 3 parents. The whole idea is we don't want to graph a parent, we don't want to graph a family, we want to graph a child. But to get to the child's data, you have to go through the parent, then to the family, and then get to the child. So we're going to eventually only have to graph 3 points still, but we're going to do it in a systematic way, one step at a time. That way I don't just choose x values, which I can go to this graph of those childs and just choose x values that I want to put in, and I'll get a y value. But I want to choose specific ones so that I can actually see the graph and see how it's changed. Have a great day.